Check, check one. Check, 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 check. Online students, can you hear me clearly? Online students, can you hear me clearly? Can someone please confirm?
Yes, sir.
Yes.
Okay, thank you. So let's start the session. This will be a bunch of small sessions actually. That means today I'll try to finish electronics and electromagnetics. We'll start with electromagnetics, but we'll see how it goes on. That means whether we'll be able to finish both, or if not, I'll finish electromagnetism maybe. Then arrange another small session to finish electronics. Like that, there were like we did some O-level seminars at different schools, so we received different feedback, like just do this lesson, that lesson, like that. Okay, so the online seminar series will be focusing on these sessions actually. Online seminar series will be focusing on these sessions. That means the things that are like when we did the O-level seminars at schools, we received different feedback. So what we'll be doing is based on that feedback, we chose what are the areas that we should teach. So we'll be teaching those areas. Okay, we'll be teaching those areas like maybe using 2 hour sessions. Okay, I think a lot of students message still. Anyways, there's a good student count. In both Zoom and YouTube Live. But we received messages from students that they find hard to join sessions at morning sometimes due to the classes. So maybe the next upcoming sessions will happen at night, maybe 8 to 10. Okay, so sessions would happen like that. And towards a bit more closer to A levels, bit more closer to O levels, bit more closer to O levels. We'll be doing another session, another question series. We have prepared a O level seminar book. Okay, we'll be doing O level. We have prepared an O-level seminar book. We'll provide that and we'll do a full syllabus revision quickly, and we'll go through a bunch of questions when it is close to O-level. So there's multiple sessions happening in the upcoming 2-3 months. So we'll inform about that, and all the sessions and all the books and everything will be available in the WhatsApp groups. So please join the WhatsApp groups. If you are not in the WhatsApp groups, send a message to this number, uh, 070 154 6825. 070 154 6825. Send a message to this number. Okay, send a message to this number to receive the uh, to receive maybe the tunes, or maybe to join the groups and to get other information. So I'll start with electromagnetism. Okay. So online students, please let us know if there's any issue with sounds or anything, or is it okay to go so that we can start. Okay, so just let us know if you find any difficulties. Okay, I mean, usually we do like 4 hour, 5 hour sessions when you are doing physical sessions at school, but I don't think you have a 4 hour, 5 hour attention span when you're online. So that's why we are breaking it for 2 hour smaller sessions. Okay, otherwise we are capable of doing for like, I mean, at the end of the day, I'm a A-level physics teacher, so we are capable of teaching 12 hours straight. Okay, so uh, but I think the attention span won't be enough. That's why we are breaking it into smaller sessions, 2 hour sessions. But if it so we'll be doing small 2-hour sessions maybe every week or maybe twice a week, and we'll try to finish things up. That's the plan. And when we are closer to O levels, we'll go with a question book, and we'll provide you a question book to try on, and it will cover everything. It contains the whole physics syllabus, physics in the sense science, physics part, everything. It covers everything. A small book with a short note and a bunch of questions. Okay, a small book, and it contains a small, like a short note of everything, and some revision. So we'll provide that also in the group so that you can try them, then join the seminar, uh, upcoming seminars for question sessions. So just contact this number. You can get everything through this number, and you can join the group. Okay, so let's start. Let's start with the session. I'll be starting with electromagnetism and electromagnetic induction, and directly we'll move to electronics after that if time doesn't permit. uh, Maybe tomorrow night or somewhere like that, as an online lesson, I'll continue the electronics part. Okay, so we'll just do sessions whenever possible. Okay, so like, and some questions were about me. I'm Janidu. I'm an engineer and A level physics tutor. So let's continue. So you have a rough idea about magnetism. Okay, you have a rough idea about magnetism. I'm just focusing on important facts only. Okay, uh, and when we are talking about magnetism, there are two types of magnetism: electromagnetism and permanent magnets. That means you can find stones which are capable of attracting magnets. You can find some types of stones that are capable of attracting magnets. Or metal particles that we call permanent magnets. Okay, that we call permanent magnets. And at the same time, we have electromagnets, because there's a lot of thousands of applications when it comes to magnets. Like for an example, you have seen there are containers, like at the harbor, how they handle containers. Okay, they have a system that they turn on and a magnet. Then when you turn on the magnet, what may happen is it will attract the any metal part such as containers. It will attract any metal part such as containers. Then what may happen is now you are now you can handle the container, but now whenever you need to drop the container, okay, now whenever you need to drop the container, you can release it. Clear? Whenever you need to drop the container, you can release it. For that you can't use a permanent magnet, right? For that you can't use a permanent magnet. For that you need some kind of a different solution. Okay, for that you need some kind of a different solution, because you need the magnetism whenever you need that, but whenever you need to get rid of magnetism, you have to drop that. So for that we use electromagnets. Electromagnets, in the sense, things are there are systems that are capable of providing a magnetism. There are systems that are capable of providing a magnetism, uh, like based on the current flow through that. Okay, based on the current flow that means when you provide a current through a system, it turns into a magnet. When you get rid of that current, it loses its ability to attract metals. Okay, so magnetic fields you have seen. Like you have the north and south. Okay, you see, usually the magnetic field we draw like this, going away from the north, collected at the south, going like this. And you have seen these kind of diagrams, and even at the center of even in the earth itself, there's a permanent magnet inside. Okay, it's not actually a magnet, it's a bunch bunch of material. It's a bunch of material collected in a way that it produces a magnet. Okay, bunch of material. We know that in Earth we have a metal core. We have a metal core. There's a lot of metal at the middle. So those metals and other minerals together, they produce a magnet. Okay, so there are different types of magnets too. Okay, there are different types of magnets too. Okay, you need to dodge down the points. About that, you actually don't need to write anything. I usually keep up a certain speed, but I'll provide you a note. Okay, I'll provide you a note. You can use that note to study everything. All the definitions and everything is included in that. Okay, so I'll provide you a note after the session. That note contains everything you need to know, even the definitions and everything. So you don't have to worry about writing down anything. Okay, you don't have to worry about writing down anything. Everything will be included in that short note. Okay, so just focus on listening. Don't worry about writing. Okay, so we have permanent magnets and we have electromagnets. Then the next thing is, okay, then the next thing is we should know a method. Okay, we should know a method to find the or the draw magnetic fields, to find the directions of magnetic fields. Okay, so usually magnetic field is a field. Okay, magnetic field is a field that occurs due to the movement of current in a system. In a system, if a current flows in a system, okay, if a current flows in a system, okay, due to this current, okay, due to this current, a magnetic field appears. Okay, due to this current, a magnetic field appears. Then you may ask, how can we have permanent magnets then? You don't, permanent magnet is just a stone, right? Permanent magnets is just a stone, right? So how do we have the current going in a permanent magnet? Actually, even in permanent magnets, you have electrons going here and there. Okay, you know that, right? Every material is made of electrons and protons. You have electrons going here and there. They produce a collective current. Okay, these movements of electrons inside this, they produce a certain current. Due to that, you have a permanent magnetism. Okay, so whenever you have magnetism, what happens is the charge is flowing somewhere. That means you have a current. Okay, whenever you have a current, okay, whenever you have a current, current is capable of producing a magnetism. Clear? Current is capable of producing a magnetism. So how can I find the direction of this magnetic field due to this current? There are two methods, right hand grip rule and Maxwell's corkscrew rule, right? So what are these rules? uh, right hand grip rule is much easier from my point of view. You just take your right hand, you just aim your thumb, you aim your thumb in the direction of current. You aim your thumb in the direction of current, then the other fingers will show the direction of the electromagnetic field you have around that. Clear? Other fingers will show the direction of the electromagnetic field you have around that. Clear? So according to this, if this is the current, the other fingers will show how the electromagnetic field goes. So in this case, it goes like this. Okay, in this case it goes like this, around this, like this. Clear? Got the idea? Okay, so this is how you get the direction of electromagnetic field around a current. Okay, so the next thing is like the next one is actually you have another law, Maxwell's corkscrew rule. That means when you when you are rotating a screw, okay, when you are rotating a screw, there's a standard direction of rotation for screws, okay. That means if you are rotating a screw, how are you going to do that is like this, right? If you are rotating a screw, you will rotate it like this, right? Clear? So if that screw moves in the direction of current, how you should rotate your hand, that is the direction of the electromagnetic field. Clear? That means if you need to move your screw in this direction, you should rotate your hand like this, right? You should rotate your hand like this, okay. Clear? So that means the way you rotate your hand, the direction you rotate your hand shows you the direction of the electromagnetic field. Clear? It shows you the direction of electromagnetic field, okay. So it may go like two rules. Right hand grip rule, you send your thumb in the direction of current, you send your thumb in the direction of current, then your other fingers will show the direction of uh, electromagnetic field. Clear? Okay. So moving forward, just let me know if you find anything difficult to understand. I can explain things again. Okay. And everything, you don't have to worry about writing a note. Everything will be included in the tute we provide. Okay. So like there are some experiments too. I'll come to that experiments later because I have included those experiments as questions. Okay. First, I'm trying to highlight on the difficult parts. These are not actually the difficult parts. How the motor works, how the like DC generator works, those kind of difficult parts that you should have a proper understanding. I would try to focus on those areas a lot. Okay. So now this is like this. Electromagnetism or magnetism occurs as a result of current, and at the same time it's capable of providing a force on a current. Okay, that means this is produced by current. Electromagnetism is generated as a result of current, and it is capable of creating a force on a current. Okay, it's capable of creating a force on a current. Okay, that means if you have a, I mean, just know this, I think you know this, right? If something goes into the board, you draw it like this. If something comes out from the board, you draw it like this. Okay, that means uh, usually if current goes like this, you can draw it like this. If current goes like this, you can draw it like this. But if something goes into the board, you draw it like this. If something goes into the board, if something moves like this, you draw it like this. If something comes out of the board, you draw it like this. Clear? If something comes out of the board, you draw it like this. Clear? Okay. Then uh, um, so when there's a magnetic field like that, assume there's a magnetic field like this going into the board. There's a magnetic field like this going into the board in this area. If you have a wire carrying a current like this, if you have a wire carrying a current like this magnetic field may create a force on this current. This magnetic field will create a force on this current. How are you going to get that? Using Fleming's left hand rule. Using Fleming's left hand rule. So what is Fleming's left hand rule? You take the middle finger, it goes in the direction of current. You take the middle finger, it goes in the direction of current. It goes in the direction of current. Middle finger goes in the direction of current. Then you get the magnetic field. Magnetic field, it goes in the direction, I mean, you can take the index finger, it goes in the direction of the magnetic field. It goes in the direction of the magnetic field. Then your thumb gives you the direction of force appearing on this conductor. So this will be the direction of force. Clear? So if you have a magnetic field in this direction, if you have a magnetic field in this direction, and if you have a current in this direction, if you have a current in this direction, again, try to get the answer. Try to draw the direction. What is the direction? Take your left hand and like, you don't like, I mean, 99% of the errors, if they ask this kind of stuff, students make is they just mess up the right hand and left hand. These kind of errors are the things that actually happen in an exam, okay? Okay, not the most difficult questions, okay? Not the all the calculation related difficult questions you will find hard. Usually students may find it hard to figure out the right hand, figure out the left hand. Okay, I mean, even when we are teaching in A levels one time, okay, when we have magnetic fields to the depth in A level science syllabus, A level physics syllabus. So when we have this Fleming's left hand rule and everything, so another student just came to me and asked, okay, now I'm giving one answer, the other student is giving an entirely different answer. So he's placing his hand like this and asking a bunch of questions. Now I can't figure out what is wrong. He can't figure out what is wrong. There's no actual issue we are finding. His method is correct. My method is also correct, but we are getting two answers. But the problem has been he's holding his fingers like this, not like this. Okay, so small issues that may occur. Okay, small issues that may occur. I was trying to figure out the issue for half an hour. He's trying to figure out the error for half an hour, but the only issue is the fingers should be placed like this. He's placing his fingers like this. So when I look at his hand, he is correct. When I look at my hand, I'm correct. I mean, no one's capable of finding the real issue. Okay, so be careful on this. Okay, be careful on this. You have to place them in correct order. Don't flip your fingers like this. Okay, so moving forward. Okay, so what is the direction of force on this guy? So current flows in this direction. Current flows in this direction. Okay, then magnetic field goes in this direction. Current goes like this, magnetic field goes like this, current like this, magnetic field like this. Then your thumb will show the direction of force. Then your thumb will show the direction of force. It is this, right? Your thumb will show the direction of force. So the direction of force will be this. Direction of force will be this. Out from the board. Out from the board. Clear? Got the idea? And what about the magnitude of this force? What about the magnitude of this force? Talking about the magnitude of this force, how strong this force is, how strong this force is, the magnitude of this force, it depends on three factors. Magnitude of this force depends on three factors. What are the factors? One is the magnitude of this current. One is the magnitude of this current. And the next one is the magnitude of this magnetic field, how strong the magnetic field is, magnitude of this magnetic field, magnitude of this current, and the other one is the length of this conductor. Definitely the length of this conductor. Clear? How long this conductor is. Clear? So what are the three factors? What are the three factors? Magnitude of the current going through this, magnitude of the magnetic field going here, and the length of this conductor. Clear? Length of this conductor. Okay. So there are a few nice examples like loudspeaker and microphone. Again, I'll move to that a bit later. using a video, I'll try to explain it a lot. Okay. So we are moving to a very important part, the direct current motor. One of them, like, so now we know that the magnetism and current together can create a force. Magnetism and current together can create a force. So they needed to use this for mechanical advantage. Okay, they needed to use this for mechanical advantage. That means to run industries. They needed to run industries. So they figured out a method to provide a magnetic field, provide a current, and using that create a rotation. Using that create a rotation. Clear? They figured out a method to provide a magnetic field, to provide a current, and using that to create a rotation. Clear? So, to explain that properly, first of all, uh, let's take this one first. You have a north here and you have a south here. You have a north here and you have a south here. Okay. Here you have a current going into the board like this. Here you have a current going into the board like this. Here you have current coming out of the board like this. Here you have current going into the board. Here you have current coming out of the board. This is north and this is south, and the magnetic field may go like this from north to south. Magnetic field may go like this from north to south, right? We always know that magnetic field goes from north to south. Here a current goes into the board. Here a current comes out of the board. Okay. So quickly mark the direction of forces on this guy and this guy. Quickly mark the direction of force on this one and this one. Just roughly write down everything in your books, okay, or just take a piece of paper. At the end, everything will be provided as a proper tute. Okay, so you don't have to worry about writing down things. Okay, you don't have to worry about writing down things, and ask questions if you need me to repeat anything. Okay, ask questions if you need to repeat anything, Fleming's left hand rule or anything like that. Just ask if you need me to repeat. Okay, just feel free to put down messages in the about the left hand right hand rule. Yeah, I'll explain the right hand rule next. I'll explain the right hand rule next. Then based on that, um, I'll explain how to identify them properly and everything, how to remember them. Okay, then the tute some students are asking will be available in the WhatsApp groups. So what may happen is we'll provide you the tute again, tute today. After providing the tute, you can go through the tute and for all the upcoming sessions, okay? For all the upcoming sessions, we'll be using that tute, okay? We'll be using that tute. It may contain questions, short notes, everything, the whole physics part in your science book, okay? The whole physics part in your science book is covered through that, okay? So I mean, you will find, uh, like you will find it convenient to study that instead of your main science book. I think this just has a summarized version of everything and the things you should remember for O level. So how should we mark the direction of forces? Yeah, Fleming's left hand rule. Okay, sure, sure. Okay, there are a few questions. I'll answer that while answering this question. Again, if something goes into the board, you draw a cross like this. If something comes out of the board, you draw a dot like this. The meaning of this is how an arrow looks like, okay? How an actual arrow, okay? How an actual arrow looks like when it goes in this direction. This is how you see an arrow from behind, okay? This is how you see an arrow from the front, the point edge of the arrow. So if an arrow comes like this, you draw a dot. That means if something comes out of the board, you draw a dot. If something goes into the board, you draw a cross. Clear? If something goes into the board, you draw a cross. Clear? That is the idea. Okay. So now I think that's clear. Now about again Fleming's left hand rule. Okay, Fleming's left hand rule. So first, this is from north to south. That means magnetic field goes like this. Okay. Let's start with the middle finger. It shows the current. It shows the current. Now see the current in this case. First of all, figure out whether you are confirm that you are using your left hand. Okay. Then the middle finger shows the direction of current. So now the current goes into the board. Now the current goes into the board. So you should somehow take your middle finger in the direction of current. That means into the board. Now you should take your middle finger into the board. Clear? You should take your middle finger into the board. Now you draw, you take the index one. Clear? The next one. Next one should go in the direction of what? Go in the direction of magnetic field. Magnetic field goes from north to south in this direction, right? Magnetic field goes in this direction. So you, while keeping your middle finger like that, you take your this finger, next one, from north to south in the direction of the magnetic field. This finger, middle finger, goes into the board. This one goes in the direction of the magnetic field. Goes in the direction of the magnetic field. Then when you figure out these two, your thumb will show the direction of force. Okay. Your thumb will show you the direction of the force. Clear? This will show you the direction of the force. Clear? So in this case, there will be a force acting downward. There will be a force acting downward. Clear? Then when you take the next one, current goes like this out of the board. Current goes like this out of the board. See? Current comes like this out of the board. Then the magnetic field is from north to south. Magnetic field is from north to south. Magnetic field north to south. Current out of the board. Clear? Current, the middle finger, out of the board. Magnetic field north to south. Then your thumb will show you the direction of the force. So the force will appear like this. Force will appear like this. Clear? Now is that clear? The students who ask about the direction when it goes into the board and out of the board, and the other thing, why a fan rotates in one direction despite supplying an AC supply. I'll explain that too. I'll explain that one too. So is it everything clear up to this point? Any questions? Any questions? Please let us know. Do you have any questions? Everyone who asks questions, please respond whether you understood things or not. Okay. So I'll explain things again when I'm doing questions. Okay. So things will be repeated again when we are doing questions. So what matters now is, okay, what matters now is how are we going to use these concepts and use it for actual something. How are we going to use this concept and use it for something actually useful? So, check this example, okay? Check this example. Now, see, we take a system like this. We place a north here and we place a south here. Now we place a conductor like this and let a current flow in this direction. Okay. Now as you see, this is your left hand. This is your left hand. Current goes in this direction out of the board. Magnetic field goes from here to here in this direction. Magnetic field goes from here to here in this direction. Then the force may appear in upward direction, right? Force may appear in upward direction on this conductor. Clear? Force may appear in upward direction on that conductor. Then you take another conductor in this side. Same thing happens but in the opposite direction. Current only opposite direction, right? On this one, current is in this direction. On this one, current is in this direction, right? So when you shift the direction of current, the direction of force will be opposite, right? You saw that in a previous example, right? You saw that in a previous example. Okay, see, when everything else is same, when only the direction of current is opposite, force becomes opposite. Clear? When everything else is same and when only the direction of current, when only the direction of current is opposite, the force will be opposite. Clear? So in this case, now there's a magnetic field going like this, and there's a, I mean, if I have a single conductor like this, that means I'm connecting a battery here. When I connect a battery here, current may go like this, then like this, then like this, then it may come like this, right? Then on this part, a force may appear downwards. On this part, force may appear upwards. So it will tend to rotate like this, right? Clear? It may tend to rotate like this. There you have a downward force. There you have an upward force. So things may try to rotate like this. Clear? Things may try to rotate like this. Okay? And at the end of the day, it will try to rotate like this. Clear? So when you have two forces like this, due to these two forces, this will try to rotate. So our target was this. We needed to create a rotational motion. We needed to create a rotational motion using this so that we can drive our vehicles, so that we can drive our machinery and everything. Clear? So now there's a small problem here. Okay? Now assume In a battery, you have a positive terminal and a negative terminal, right? In a battery, you have a positive terminal and a negative terminal. You connect your positive terminal to this and your negative terminal to this. Now there's a small issue. Why? See, now due to these forces, it will rotate like this. It will rotate like this. When it rotates, what's the problem? Now the positive terminal is here, negative terminal is here, right? When it rotates, even the terminals rotate with them, right? Initially, positive terminal was connected here, negative terminal was connected here. I just connect it here. Then what happens when it rotates? When it rotates, what may happen is the terminals may go like this. It will go with its connected edge, right? Now we have a small problem. What is the problem? The problem is initially in this side current was going like this. Now current goes like this when it rotates. After one half rotation, initially it was rotating like this. Initially the current was like this. So the force was in this direction. So it was rotating like this. But now after half of a cycle, now the current is in this direction. So the direction of force goes in the other direction, right? Direction of force goes in the other direction. Why? Current into the board, middle finger into the board, magnetic field north to south, magnetic field north to south, magnetic field north to south. Then the thumb downwards, see, thumb downwards. Then about the other one, it's in this direction. It's in this direction. So initially on this guy force was on upward direction, on this guy force was in downward direction. So they rotated like this. But after half of a cycle, now on this guy force is in upward direction, on this guy force is in downward direction. What is the problem? Initially it rotated like this, now it will rotate like this. Clear? Now it will rotate in opposite direction because the direction of forces changes. Okay. So now the problem you should understand. Initially you had a system like this. It rotated like this. Then the direction of current changes. That means now the positive terminal is here. So current goes like this. So the force on this guy now is in opposite direction. Now it is in downward direction. Force on other guy, this one, now it's in upward direction. So they may start rotating in the opposite direction. Now you don't need your vehicle to go like this, right? Okay. Now what is happening is it rotates like this, stops, then like this, stops, then like this, then like this. Clear? It's not going to rotate 360. It just rotates, stops. Again like this. Again like this. Clear? You don't need your vehicle to go like this, right? No one needs, right? Okay. No one needs their vehicles to move like this. So we have a problem to solve. Okay. We have a problem to solve. For that, we should figure out the reason behind the problem. What is the reason behind the problem? Reason behind the problem is this. When it rotates, the terminals, connected terminals goes with them. See, when they rotate, the connected terminals rotates with them. That is the problem. Okay, see, positive terminal was permanently connected to this. So when it rotates, positive terminal goes here. Negative terminal of the battery was permanently connected to this. So when it rotates, negative terminal goes with it. But I can somehow keep the same motion. I can somehow keep the same motion if I can somehow keep the same motion if I can remove this positive terminal here and connect it here, and if I can remove this negative terminal here and again connect it here. Clear? If I can remove this positive terminal and connect it here, and if I can remove this negative terminal and connect it here, then I can keep the same motion, right? Problem is I permanently connected this positive terminal. So when it rotates, positive terminal connected is, it changes. But when it rotates one half cycle, if I can remove the positive terminal and connect it back to this, if I can remove the negative terminal and connect it back to this, then we can keep up the rotation, right? Then we can keep up the rotation. Clear? If I can shift the terminals again. So for that we introduce what? Commutator, right? For that we introduce the commutator. It's in your book, right? For that we introduce a system called commutator. That means instead of permanently connecting the positive terminal and the negative terminal, instead of permanently connecting the positive terminal and the negative terminal, what we do is instead of permanently connecting them, okay, we connect two split ring commutators. That means we connect just two rings, not the positive terminal and negative terminal. We just connect two rings like this. Clear? Now we provide the positive terminal and negative terminals using two brushes. We connect the positive terminal like this and negative terminal like this. Okay. Instead of permanently connecting them, I use a small brush as the positive terminal. I use a small brush as the negative terminal, and they are permanently connected there. I'm not directly connecting it to the wire. Now what is best is, now when the system rotates, commutators rotates with them. So after one half cycle, this commutator will reach here, this commutator will reach here. Then every one half cycle, this commutator connects to the positive one, and this commutator, now this commutator is connected to the positive terminal and this commutator is connected to the negative terminal. But after half of a cycle, then this commutator connects this one and this commutator connects this one. Clear? After one half cycle, this commutator connects this one and this commutator gets connected with this one after one half cycle, right? Clear? Every half cycle that happens, right? Clear? The commutators shift with the terminals. So that's what I needed, right? I needed to connect the positive and negative terminal every half cycle. Then it will keep rotating. Clear? That's what I needed, okay? That's what I needed. I needed to shift the terminals. Okay, every half cycle. Clear? Every half cycle. That is the whole target of using commutators. Clear? Got the idea? So that is the target. So your electromagnetic hard disks, vehicles, fans, everything works as a result of using motors. Clear? Okay. Got the idea? Just mention in the Zoom chat. So this is the whole point of a electric motor. Okay. This is the whole point of a electric motor. You have magnetic poles. So this part we call the armature. That means it will never look like this, okay? It will never look actually like this. You will have a, I mean, this is just the model of these questions they may ask. Okay, you have a very simple motor like this. How are you going to create a powerful motor? How are you going to create a powerful motor? What are the options? What are the options? You create a system like this. More wires instead of one, you use more wires and you use a strong magnetic field around that. You use a strong magnetic field, you use more wires like that, you stack wires on top of each other and create a much stronger huge wire. Then you send a huge current, then your rotation of the motor will be much powerful. Clear? Rotation of the motor will be much powerful. This setup, and we usually buy, I mean, these things can't float, right? So you need some kind of a metal core, soft iron core we call that. You need some kind of a core. Around that core you put these strands, right? You put these strands around that core. Okay, around that core you put those strands. Okay, you bind everything around the core. That core and these bindings together we call the armature, right? We call the armature, and around that you have magnetic poles. I'm just talking about the parts you have in your textbook. Around that you will have magnetic poles. Around that you will have magnetic poles, and the commutator you already know. Okay, commutator you already know. We call them split ring commutators. Clear? We call them split ring commutators. Clear? Got the idea? Just let us know if you have any questions. Put in the Zoom chat if you have any questions. Okay. Okay. So there were some questions. Okay. There were some questions about this. Okay. I'll explain things again when others are doing questions. Okay. So the rough idea is we needed to shift the positive terminal and negative terminal every half cycle. Okay. We needed to shift the positive terminal and negative terminal every half cycle. So for that, what we used was, okay, two split ring commutators. Okay. Instead of permanently connecting the positive terminal here, instead of permanently connecting the positive terminal here, what we do is we connect two rings, two split rings. Now positive terminal is just touching this and the negative terminal is just touching this. Okay, these two terminals are just touching them. So when this system rotates, this commutator may come here, this ring may come here, this ring may come here, this ring may come here. Then this ring, which is now connected with the negative terminal, after half of the cycle, it will be touching the positive terminal. This ring, which is touching the positive terminal, after one half cycle, it will touch the negative terminal. Clear? It will touch the negative terminal. Got the idea? That's how the split ring commutators work. Okay, they allow you to shift the positive terminal and negative terminal every half cycle instead of permanently connecting them. Clear? Instead of permanently connecting them. Got the idea? Anyone? Any other questions? Every half cycle it will keep rotating now. Okay, every half cycle it will keep rotating, and the best thing is it will keep rotating in the same direction. It will keep rotating in the same direction. Okay, that means this commutator, this split ring is permanently connected to this wire, and this split ring, it is permanently connected to this wire. So when the wires are connecting, these rings may rotate with them. Okay, when the wires are rotating, the rings may rotating with them, or the commutators will be rotating with them. But the terminals will not rotate, they will stay here. So now this commutator is connected to this terminal, this commutator is connected to this terminal. So when they rotate one half cycle, now this commutator touch this terminal and this one touch this one. So it changes every half cycle. Clear? Got the idea? Instead of permanently connecting them to the wires. So like the method to connect the terminals in a way that they can shift is commutators actually. Okay. Okay. Terminals will not change. Why? Terminal is not connected to this ring. It is just touching this ring. It is just touching this ring. So it will go like this, touching the ring. Okay. The ring and the terminal just touch each other like this. They are not connected. They are not connected. They just touch each other. So the terminal will stay there and the commutators will rotate and they may come like this. They are just touching. Okay. Terminals are not connected. They are just touching the ring. Okay. They are just touching the ring. So terminals may stay there and the rings will rotate. Rings will rotate. Got the idea? And what is the reason? There's no point of clockwise and anti-clockwise shifting rotation in a motor. Why? Then your vehicle will go a bit forward, then again backwards, again bit forward, again backwards. There's no point of having that kind of a motion in a motor, right? Okay. There's no point of having that kind of a motion in a motor. Okay, you need a continuous rotation in one direction. Clear? You need a continuous rotation in one direction. Okay. So one of the most like one of the most innovative or imaginary like advancements was that Faraday thought, okay, the Faraday thought, okay, there's a magnetic field, there's a magnetic field, and there's a current, and there's a current. There's a magnetic field, and there's a current. So it provides us a motion, right? It provides us a motion. It provides us a rotation motion. So the Faraday thought, okay, you have a magnetic field, you have a current, then it rotates. If you can provide the magnetic field and provide the rotation, will it produce a current? Okay, one of the most simple, but one of the most advanced thoughts ever, okay? We are here because of this thought. Okay, we are here because of this thought. Okay, today also we haven't replaced motors by anything, right? 100% of the vehicles are using motors, everything else uses motors. Okay, so and like at the same time everything uses current, right? Everything uses current. Okay, there's nothing replace current, right? I mean, yes, we use different methods to create current, but at the end of the day all we use is current, right? Okay, there's nothing that can drive all our systems other than current, right? So what Faraday thought was, okay, we those days we didn't have a proper method to produce current. What he thought was, okay, you have a magnetic field, then you provide a current, then it rotates. What if I have the magnetic field and I rotate this? Will it produce a current? A very simple thought. Will it? And the thought was actually correct. Here comes the turbine. Here comes the DC motor. Here comes the DC generator. Okay. Here comes the dynamo. Okay. The thought was correct. It actually, when they tested, okay, actually when they provide a magnetic field, and instead of providing a current, when they provide the motion, it actually produced a current. Okay, that is the concept of DC generator. Okay, that is the concept of DC generator. I'm just changing the order that I'm teaching. Ideally, I should teach electromagnetic induction, then reach here. But the idea is it was produced based on this concept. Okay, that's how things appear. Okay. So what they prepared was this. They used a motor. But instead of sending a current through the motor, they used a system like this. Clear? They used a system like this. Then let water or something pass through that. Let water or something pass through that. Using that, they rotated the motor. Instead of providing a current, they provided the rotation to the motor, which produced a current. Okay, that's how the things started. Okay, that's how the things started. So they created a nice setup like this. Okay, they created a nice setup like this, motor but inverse motor. Okay, a motor but an inverse motor. Okay. So now they use a system like this. So now uh, they had two options. They have the option of preparing this just like the DC motor using two commutators and all, but initially they didn't do that. They just connected one side permanently to one ring, connected the other side permanently to the other ring. Okay, okay, see, that means this ash color side, is permanently connected to this ring only. This ash color side is permanently connected to this ring only. Clear? This yellow color one is permanently connected to this ring only. Clear? So now can you remember, when you don't shift them, when you permanently connect them to two sides, two terminals, when you provide the current, it rotated like this, then like this. I'm talking about the motor. It connects like this, then like this. direction of the motion changed every half cycle, right? Direction of motion changed every half cycle when you permanently connect the terminals, okay? When you permanently connect the terminals. But uh, now when you do the same with the turbine, instead of direction of motion changing, now we are providing the same motion using water or something. Current changes its direction every half cycle, okay? Now current changes its direction every half cycle. So if you connect a system like this and look at a galvanometer, you can see galvanometer changing its direction every half cycle, okay? Galvanometer changes its direction every half cycle. Every half cycle, galvanometer changes its direction, okay? It returns, and the galvanometer changes its direction every half of a cycle. See, every half cycle, galvanometer changes its direction. Initially, when we provide the same current without shifting the terminals, direction of motion changes every half cycle. Now, when we provide the same motion, instead of without changing the terminals, current will change its direction every half cycle. Clear? Current will change its direction every half cycle. So if you graph the current, you will see a graph like this. A sinusoidal graph, we call them. You will get a sinusoidal graph like this, okay? You will get a sinusoidal graph like this. That's why you are getting a sinusoidal graph from a alternative current generator. Clear? Clear? Got the idea? Because you didn't shift the terminals. You are connecting terminals permanently. Okay? You should have used two commutators like that. Then you can get rid of this issue. Okay? Then you won't get a negative half. Okay? Then you won't get a negative half. Then it will be always positive. Then it will be always positive. Okay? You have that option if you like. Okay? See, if you use a system like this, see, now this is a system with commutators and brushes. See, now you have two terminals and they are just brushes. Now these two terminals are just brushes. Then you use two split rings. Then every half cycle, who's touching the brush will change, right? Now they are touching like this. After one half cycle, every half cycle, which commutator touch which brush will change, right? Clear? So in a scenario like that, current will go in the same direction always, okay? In a scenario like that, see, even in the DC motor, this is a nice example. Even in the DC motor, this is how the split rings work, okay? This is how the split rings work in a DC motor and a DC generator too. In a DC generator too, see, they shift every half cycle. See, now this commutator is touching this one. Now this commutator is touching this one. See, they shift every half of a cycle. Clear? They shift every half of a cycle. Then you won't get a positive and negative graph. Okay? Then you won't get a positive and negative graph. You will get a continuous positive graph like this. It will not go in the positive direction. It will not go in the negative direction. It will continuously be in the positive direction. Clear? Got the idea? Clear? So that is the idea of a AC generator. Okay, that is the idea of a AC generator. And this process of creating current, using motion, what do we call that? This process of creating current using motion, what do we call that? We call that the electromagnetic induction. We call that electromagnetic induction. The process of creating current using a motion, we call that electromagnetic induction. So again, what decides the strength of this electromagnetic induction? How much of a current can I produce? how much of a current can I produce? Who decides the strength of this electromagnetic induction? How much of a current can I produce? The number of turns here. Just like in the DC motor, instead of one turn, we can use multiple turns. Instead of one wire, we can use multiple wires. So how many wires are there? Okay. And how strong the magnet is. Higher the strength of the magnetic field, okay, higher the strength of the magnetic field, okay, more stronger the magnetic field, okay, stronger the magnetic field, stronger the current you produce, stronger the current you produced. And the next one is, how fast is it rotating? How fast is it rotating? How fast does it move? Okay, how fast does it move? Clear? Got the idea? Got the idea? Okay, just ask questions if you have any. Yes, it will be a DC current. If the current doesn't go in the negative direction, we can call it a DC current. Okay, let's move forward. Okay, let's move forward. Okay, and the idea was, there are some one people were requesting some other lessons. The idea is actually, yes, we received the required comments from a lot of students when we were doing physical seminars. So what we are going to do is, whenever possible, we'll do every part, like we'll try to finish each part, and towards A levels we'll discuss all the questions in the tudes given to you, okay, and the tudes will be provided today in the WhatsApp group. Okay, we'll use one single tude, one huge short notebook. We use that short notebook to continue things. Okay, we'll use that short note tude to continue things one by one, okay, to finish things up, and you can use that to study everything. Okay, you can it contains a good short note to revise everything quickly. Okay. So electromagnetic induction, you can't just simply learn and get rid of this like this. Okay. Uh, we have to learn some like actual theorems connected to these two. Okay. We have to learn actual theorems connected to these two. Okay. So so uh, talking about electromagnetic induction. Okay. Talking about electromagnetic induction. Now, as we saw, current and magnets create a motion, then motion and a magnet create a current. That is electromagnetic induction. Motion and a magnet create a current. So the easiest example for that is this. Easiest example for that is this one. If you have a bunch of wires like this, if you connect a galvanometer here, this is just a metal rod. If you use a magnet like this, now the magnet is okay, magnet part is done. Now you should provide a motion. Now you should provide a motion. How can you provide a motion? You quickly move this magnet in this direction, clear? You quickly move this magnet in this direction, clear? When you quickly move this magnet in this direction, you will see a reading appear in this galvanometer, okay? You will see a reading appear in this galvanometer, clear? You will see a reading appear in this galvanometer, okay? Then when you move this magnet away, then when you bring it close and stop it, when you bring it close and stop it, again the galvanometer reading will go to 0. Why? When you bring it closer, there's a motion and a magnet, then it's okay. But when you bring it close and stop it, there's no motion. There's no motion. So galvanometer reading will go to 0, or the ammeter reading will go to 0. That means there's no current. There's no current. Now when you move that again back, when you move that back again there's a magnetic field and there's a motion. Whenever there's a magnetic field and a motion, there's a current. So again the galvanometer will shift, but in the other direction, because now you're taking it away. So the idea is, when it is stopped closer or further, no reading. When you move it, there's a reading. Why? Magnets itself can't produce a current. You need a magnet and a motion. Clear? You need some kind of a magnet and a motion to produce a current. Okay. So the theorem behind this is, okay, right hand grip rule. Okay. Theorem behind this is right hand grip rule. Okay. So sorry, Fleming's right hand rule. Sorry about that. It's Fleming's right hand rule. What is Fleming's right hand rule? You take your right hand. Now assume that there's a magnetic field in this direction. And there's a magnetic field in this direction like this. Okay. There's a magnetic field in this direction. And there's a conductor moving like this. There's a conductor moving like this. Clear? There's a conductor moving like this. A conductor moving in this direction. Clear? There's a conductor moving in this direction. So you take your right hand. Now you aim your thumb in the direction of motion. So your thumb goes in this direction. You aim your thumb in the direction of motion. Clear? So your thumb goes in this direction. Clear? Then you take your next finger. You aim it in the direction of the magnetic field. So thumb in the direction of motion. This one in the direction of magnetic field. This one in the direction of magnetic field. And the next one, the middle finger, will show the direction of the produced current. The middle finger will show you the direction of the produced current. So in this case, current comes out of the board. In this case, current comes out of the board. Clear? Here, the motion in this direction, magnetic field in this direction. Here, current comes out of the board. Clear? That is the idea. Okay. So even in a like even in a DC generator, that's what happens. Okay. This is, I think, the example you have in your book. Okay. This is the example you have in your textbook, I think, right? Is this your textbook? Yes, right? Yeah. So uh, you take your right hand. You take your right hand. I'm talking about this red color one. I'm talking about this red color one. You have a magnetic field in this direction. Okay. You have a this is the, but sorry, this is the, yeah, this is the dynamo. So we can go with this. So what is happening is you aim your thumb, in the direction of motion. Okay. You aim your thumb in the direction of motion. If it goes up like this is the direction of motion. You aim your index in the direction of magnetic field. Then your middle finger shows the direction of the current. Okay. That is the idea. I'll go to that animation. It will be much convenient. Okay. Apply right hand grip rule on this. Check what is the direction of current on the yellow color one and what is the direction of current in the ash color one. Assuming that it's rotating in this direction. Assume that this is rotating in this direction. Assuming that this is rotating like this. Find the direction of current in the yellow color side. That means this wire that comes out of this and connected to this one, and the ash color side which is connected to blue terminal. Check the direction of currents. So now the books will be available in the WhatsApp group and the Zoom chat. Okay. We'll use that for questions. Okay. Now check. What about this one? Take your right hand. This yellow color one goes in upward direction, right? In this case, the yellow color one, if it rotates like this, the yellow color side goes in upward direction. Thumb in the direction of motion. Then next one, from north to south, magnetic field from north to south, clear? So the next one shows the direction of current. That means current goes into the board. Current goes into the board. So what happens is in this terminal, current goes into the board. Clear? Then go to the next one. If the system is rotating like this, okay, if the system is rotating like this ash color side goes down, right? This ash color side goes down, clear? Ash color side goes down. So again, you take your right hand, motion is downward, clear? Motion is downward. Then magnetic field is from north to south, okay? Motion is downward, okay? Motion is downward. Magnetic field is from north to south. Motion of ash color side down. This one from north to south. Then current comes out of the board. Okay. Current comes out of the board. Clear? Clear? Okay. In A level physics, you have a much complex magnetic field lesson and beware of your hand. Okay, we have some scenarios like students getting their hand fractured in the when writing A levels, trying to apply uh, right hand rule and the left hand rule. Okay, so be careful about that. You can just skip the question if you are not good with that. Okay, so yeah, so what happens is here current goes in, here current comes out. That means what would be the path of the current? Current will go like this into the board, would rotate like this and come out of the board and return like this. Clear? Current may go like this, go in this path, go in this path, then return, 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 then to the positive terminal. See? That's what happens. Clear? After 1/2 cycle, things may change a bit. Clear? That is the whole target. Okay? Clear? So that's the main idea behind electromagnetic induction. Okay, that's the main idea behind electromagnetic induction. Okay, so one more part we have to learn about transformers. Actually, we have to learn about transformers. Before that, yeah, there's a few questions that we should try, but even the questions contains transformers, so I think it's convenient to start with transformers. But let's do this example. Okay. Let's do this example. Then let's try to move forward because this is available in your note. So definitely you have to know this available in your note in the sense it's available in your main book, O-level science book. This example, right? Quickly do this. A very simple question. Quickly get answers to this. I think the tunes are now available in the WhatsApp groups, right? Tunes are available in the WhatsApp groups. And tunes will be are available in the Zoom chat too. Okay, tunes are available in the both WhatsApp groups and uh, Zoom chat. In the English medium tute, this is around 77 or 78 page. Check for the page number. I think it is 77 in the page 77. Okay, try this. Try this question quickly. And put down the answers in the Zoom chat. Okay, put down the answers in the Zoom chat and the YouTube live chat. This is a simple one. This was there in your tute. In your, not in the tute, actual your science book. Mali, provide the tunes in the Zoom chat. Tunes are available in the Zoom chat and in the WhatsApp groups. If you are not in the WhatsApp group, contact the given number to join the WhatsApp group, okay? 070-154-6825. And just request for the tunes now through that WhatsApp number, okay? 070-154-6825. 070-154-6825. Otherwise, things are available in the Zoom chat and the WhatsApp groups. If you can't find them, let me know in the Zoom chat or in the YouTube live chat. So, how can I get the answers? Quickly put down the answers in the Zoom chat. So let's start. Take this conductor. The current flow in this conductor is in this direction, right? Current flow in this conductor should be in this direction. Why? Right hand grip rule, right hand grip rule. Current is in this direction. Then only the magnetic field may appear in this direction, right? If the current goes in this direction, magnetic field may appear like this. Magnetic field may appear in this direction. Clear? So what is the direction in which the current should flow through the wire to form the magnetic field shown in figure 1? It is in upward direction. It is in upward direction. Which rule do you use to determine the direction of the current in figure 1 above? For me, it is right hand grip rule. For me, it is right hand grip rule. Okay. Then in figure 2, what is the direction of current flow when the switch is closed? Okay. In figure 2, when you close this switch, the battery is connected like this, positive terminal, negative terminal, right? Battery is connected like this. This is the positive terminal and this is the negative terminal. So the current should go in this direction, right? Current should flow like this. Current should flow like this. Clear? So inside this conductor, it's in this direction. Clear? Inside this conductor, it's in this direction. Clear? So current may flow in this conductor in this direction from B to A. From B to A. From current may flow from B to A. From B to A. What is the direction of the movement of the AB rod based on this? So now here you have the north and here you have the south. Magnetic field appears from north to south. That means in downward direction. Clear? Magnetic field appears from north to south. That means in downward direction. Clear? So the thing is, current goes like this from B to A. Current goes like this from B to A. Then what is the hand you use? Left hand. Okay. Current, middle finger, current, middle finger going like this. Magnetic field north to south, downwards. So current in this direction, magnetic field north to south in downward direction. Current B to A, magnetic field downward. Then the motion is given from this, or the force is given from this. It is in this direction. it is in this direction, right? Clear? So the movement will be in this direction. Movement will be in this direction. Clear? It will move towards this wall. Clear? It will move towards this wall. Next one, write down the two strategies that can be used to increase the speed of the motion of AB. They need us to find two strategies to increase the motion, I think, right? So what is the direction of the movement of the AB rod? In this direction, right? You can write towards this wall or away from the magnet. You can write here away from the magnet. Clear? It's going away from the magnet. Clear? Then the last one, write down two strategies that can be used to increase the speed of the motion of the AB rod. Write down two strategies that can be used to increase the speed of the motion of the rod of the AB rod. What are the two strategies that can be used to increase the speed? From you can use what are the three factors that decide the strength of this motion? Strength of the magnetic field, strength of the current, magnitude of the current. Then the other one is the length of the rod. Length of the rod. One thing to tell is there's no point of having a rod like this, okay? Why? Why? Length of the rod doesn't matter in this scenario. Why? Length of the rod means the length of the rod that goes through the magnetic field, okay? A force will appear on the part that goes through the magnetic field only, okay? So having a long rod like this won't help here, okay? Okay, the length of the rod, but if you write it properly, it's the length of the conductor that goes through the magnetic field, okay? That you have to understand. So when you're writing the answer also, try to write it properly. What decides this? Magnitude of the current, strength of the magnetic field. Then the other one is length of the conductor that goes through the magnetic field, okay? Having a huge conductor but a small magnetic field won't help, okay? Okay, so here you have to change the magnet too. Otherwise changing the length of the rod won't help. So don't write the answer as length of the rod in this scenario, okay? Okay, don't write the answer as increase in the length of the rod. Okay, no support here. Why? The magnetic field is limited in this area only, okay? So you have to write in this case increase in the current, that means use better batteries and increase the current. That is one thing. Increase the current, that means use better batteries. Then the other one would be use a strong magnet. Use a much strong magnet. Clear? Use a much strong magnet. These are the, from my point of view, these are the methods to increase the motion. Clear? Okay. Okay. Clear everything up to this point? Okay. Write down if you have to write anything. Let's learn about the microphone and the loudspeaker. Two examples available in your textbook. Okay. And my target in theory sessions is understanding, make sure you understand all the small theory points properly so that you can handle anything in that lesson, okay? Then towards the question sessions, okay, when it is close to O levels, towards the question sessions, we'll just jump through the theory very fast and do a few questions to make sure you are comfortable with questions, okay? That is the target. You can try the whole tute, okay? We'll provide you the answer scripts too, okay? We'll provide you the answer scripts too, and in future discussions also may happen, okay? So through that, the physics part, you can without any issue, you can like resolve any physics issues you have, okay, from the book and the sessions going on, okay, because it contains almost all the important information, okay, because it contains almost all the required important information you need for uh, O levels, okay. So I think everything's clear up to this point, right? Okay. So if we move forward, okay, if we move forward, small theory parts are remaining to do. One is one is okay. Let's learn both the scenarios at the same time, okay? Let's learn both the scenarios at the same time. There's the mic and there's the loudspeaker, okay? There's the mic and there's the loudspeaker, okay? So when you speak to a mic, okay? When you speak to a mic, what happens? When you speak to a mic, what happens? See, you're like when you speak, what you do is you provide a motion to air particles, right? You provide a motion to air particles. So that may trigger a motion on the diaphragm. Okay, your voice will trigger a motion in the diaphragm. Clear? So based on that, see, a conductor will move. Based on that, a conductor will move. Clear? And around this, what you have is a north and a south. Around this, what you have is a north and a south, a magnet. Clear? Around this, you have a magnet. Now you know a motion and a magnet produce current. Motion and a magnet produce current, right? A motion and a magnet produce current. So a current will be formed in this, see? Clear? A current will be formed in this based on the shape you are speaking. Based on the shape you are speaking, current will be formed here. Got the idea? You speak to this, okay? You speak to this, which will move the conductor, which will move the conductor. It is a conductor moving in a magnetic field according to the voice you make. Because based on the voice, this diaphragm may move. Okay? Based on that, the conductor may move. So the movement of the conductor depends on my voice. So the signal will also depend on my voice, the way I speak. Clear? It will depend on the way I speak. Clear? Got the idea? So this signal, what we do is there's an amplifier, audio amplifiers. This signal is very weak, okay? This signal is very weak. It is sent to an amplifier to improve this pattern, okay? This is sent to an amplifier. This is an amplifier. It takes this weak signal, provide energy to that, and amplify that signal with a lot of strength, Then it is sent to a loudspeaker. What is a loudspeaker? Just, we call this moving coil loudspeaker. We call this moving coil loudspeaker. If we break it into parts, what you have is, again, see, a magnet, a coil inside that, and a diaphragm that moves. A diaphragm that can push air. A coil, a magnet around that, and a diaphragm that move that. Clear? Diaphragm that can move that. So what happens is that signal we produced goes through this coil. It goes through this coil. Now there's a current and a magnet which produce a motion. Now there's a current and a magnet. When there's a current and a magnet, it produces a motion or it produces a force. It provides a force on this diaphragm. It provides a force on this diaphragm. Clear? Based on the signal I sent. Clear? Based on the signal I sent, it produces a force on this diaphragm. Clear? This is the loudspeaker. Okay, this is the loudspeaker. Okay. So one more part to be discussed. Okay, only one small part to be discussed, which is the transformers. Okay, transformers. Okay, what are transformers? What are transformers? Again the same scenario. Okay, again the same scenario. In a transformer, what happens is you have a primary coil and you have a secondary coil. You have a primary coil and a secondary coil. Okay, what happens from this primary coil and secondary coil? When I send a current to this, see, there's a current. Okay, so a current can produce a magnetic field. Can you remember? A current in a conductor can produce a magnetic field. So it creates a magnetic field like this. It creates a magnetic field like this. Clear? Clear? So we use this method. Okay, we use proper methods to make sure that the whole magnetic field goes like this. Okay, I mean, ideally if you have something like this, it will produce a magnetic field like this and it will spread. Okay, it will spread like this. Okay, but in transformers we use a special method to make sure that this whole magnetic field drives through this. Clear? We make sure that this whole magnetic field drives through this. Clear? So in a transformer, what we do is we make sure that the whole magnetic field produced will go through this. Clear? Now I need to generate a current here. I need to generate a current. What do we need to generate a current? A magnetic field and a motion. We need a magnetic field and a motion to produce a current. But here I don't have a motion. See? Here I don't have a motion. Here I have a magnetic field. Here I have a magnetic field. But I don't have a motion. So I can't create a current, right? So as a result, if you produce a DC current, you won't get a current in this side in a transformer. But instead of that, we send a changing current to transformer. So from a DC current, you can't do anything. Why? A DC current into this will produce a magnetic field, but there's only magnetic field, no motion. Magnetic field itself can't produce a current. You need a magnetic field and a motion. Clear? You need a magnetic field and a motion to produce current. Clear? You need both. You need a magnetic field and a motion both to produce current. Clear? So in this case, you produce a current, but no, so it creates a magnetic field. But in this case, there's only magnetic field, no motion. But we mimic the motion by varying the magnetic field now. That means what happens when you are moving something is the field that felt by that conductor changes. Okay, that means what we actually need is not a motion and a magnetic field. What we need is a changing magnetic field. In many other scenarios, what we did was we provide a magnetic field and we let the conductor go through that. We create a magnetic field and we let the conductor go through that, which mimics a changing magnetic field. So what actually produces a current is a changing magnetic field. That means a magnetic field and a motion, which produce a change in magnetic field. Here in a transformer, since we can't produce the motion, we change the magnetic field. We directly give a changing magnetic field. How? We provide a changing current here. When the current here changes, the magnetic field changes, its magnitude changes. So a changing magnetic field will produce a current. So you will have a current here. Clear? We call the current go through this primary current IP. We call the current through this as the secondary current IS. Clear? So IP and IS, primary current and the secondary current. Clear? We call this the primary current and we call this the secondary current. Clear? And there are two equations that dominate. When there's a current, there will be a voltage between these two terminals. We call this the primary voltage. We call this the secondary voltage. We call this the primary voltage and we call this the secondary voltage. Then there are two equations that dominate this. In a transformer, there will be a certain rounds of strands here, right? Certain number of rounds here. Certain number of rounds here. This number of rounds we call N primary. N primary. This we call N secondary. Clear? This is N primary. This is N secondary. Clear? Primary rounds, number of primary rounds. This is number of secondary rounds. And the connections between them is Vp over Vs. Primary voltage over secondary voltage is equal to the number of primary rounds and number of secondary rounds. Okay. We can't prove this. We need Faraday's law to prove this. You don't have the Faraday's law in O level, so you just have to study this. Okay. V primary over V secondary. V primary over V secondary equals N primary over N secondary. That means the voltage is proportional to the number of rounds in that side. Clear? So based on this, there are two types of transformers. Step up, step down. That means if I change both the sides, I get Vs over Vp equals Ns over Np. Vs over Vp equals Ns over Np. So in this case, number of the secondary voltage is proportional to the secondary number of rounds. So in some scenarios, this is higher. In some scenarios, this is higher than this. Ns is higher. Then Vs will be higher, right? If Ns is high, Vs will be high, right? Clear? That means if Ns is larger than Np, then Vs will be larger than Vp. Clear? If Ns is larger than Np, then Vs will be larger than Vp. Clear? So in this case, we call this, in this case, okay, in this case, secondary voltage is larger than primary voltage. We call this a step-up transformer. That means the secondary voltage you receive is larger than the voltage you give. The secondary voltage you receive is larger than the voltage you give. Then in some scenarios, the primary number of rounds is large, then the V primary is large. That means in some scenarios, N primary is larger than N secondary, then V primary is larger than V secondary. Clear? V primary is larger than V secondary in that case. Clear? So in a scenario like this, okay, primary voltage will be higher than secondary voltage. Clear? That means you receive a smaller voltage than you give. You receive a smaller voltage than you provide to the system. We call them step down transformers. Clear? We call them step down transformers. Then from this equation you can get the voltage. Again you have a relationship Vp Ip is equal to Vs Is. Do you have P equals Vi equation in your O-level syllabus? P equals Vi? No, right? Power equals voltage into current? Yes? Power equals voltage into current. Do you have that? No. Yeah. So this is derived using that. So that also you don't have to know the proof. Just know the equation. V primary into I primary is equal to V secondary into I secondary. Okay. These two equations you should know connect about a transformer. Okay. Vp Ip equals what? Vs Is. Vp Ip equals Vs Is. Then Vp over Vs equals Np over Ns. Okay. Yes, if given that the magnetic field is wide, increase in the length is useful. Yes. Okay, you have P equals Vi in all of us, right? Okay. So then this is derived. Okay, this is derived using that. Okay. This is derived using that. P equals Vi is included in your O-level syllabus. So this is VPIP means the power you give to the primary side. This is the power you give to the primary side, VPIP. It is equal to the power you receive from the secondary side. That means no energy is lost. You give a certain power, VPIP, you receive the same power from this side, VSIS. Clear? You give a certain power to the transformer, you receive the same power out from the transformer. Clear? You give a power, you receive the same power. VPIP equals VSIS. Clear? VPIP equals VSIS. Primary power you give to the system is equal to the secondary power you get out of the system. Clear? VPIP equals VSIS. Clear? Okay. Okay. This is the idea. VPIP equals VSIS. So this is about transformers. Okay. This is about transformers. Transformers can be made in using different methods. Okay. Check this. Check this. Quickly go through this. It's in the question. It's in page in your tute, page 77. I'll finish the session within 5 minutes. Okay. I'll do these questions and finish the session. Okay. Question 1. Quickly go through the question. So like if I explain roughly, name state whether there is a deflection in the galvanometer in the following instance. So this is another transform, okay, see, some number of rounds and another number of rounds, see, this is actually a transform, right? See, a set of rounds, a set of rounds. So to get a reading in galvanometer, what should you do now? Now you know. What should you do? You should create a change here. You should create a change here. Giving a current itself is not enough. You should give a change in current. Okay. You should give a change in current. Okay. So what you do is, when closing the switch, what happens? Yes, definitely when you close the switch, a current will appear in the galvanometer. Why? When you close the switch, what happens is it's a change in current. Current was not there. Now all of a sudden there's a current. That means it is a change in current, right? That means it is a change in current. Okay. So a change in current, okay. A change in current will always create a galvanometer reading, okay. A change in current will always create a galvanometer reading, okay. So again, when the switch is kept closed, no, why? When the switch is closed, the same current is moving continuously. Same current is moving continuously, which does not create a change. Which does not create a change. When there is no change, a current will not appear in the secondary. So galvanometer reading will be continuously 0. But now there's a current, all of a sudden you open the switch, which is a change. All of a sudden you open a switch, which is a change. It's like when you removing the magnet away from that initial example. Can you remember? Can you remember in that initial example, uh, when there's a coil like this and a galvanometer like this, when you move the magnet away from this, there was a reading in the galvanometer. It's like you are removing the magnet away. So opening the switch is same, right? Opening the switch means there was a field. You get rid of the field. You take it away, which is a change of field. Which is a change of field. In a way, which is a motion and a magnetic field. Clear? We mimic in that scenario. Clear? So it is similar to removing the magnet away. So when you turn off the switch, it's like getting the magnet away. Again, a change in magnetic field. A change in magnetic field will create a galvanometer reading always. Clear? Because it produces a current. Clear? It produces a current. Got the idea? It produces a current. Okay. So yes, this C yes, A yes, B no. Clear? Out of M1 and M2 insulated copper coils, which coils are used as primary and secondary. Now you can see here we produce, here we generate. So here we produce, that means this is the primary, this is the secondary, right? So M1 is primary, M1 is primary, M1 is primary, M2 is secondary. M1 is primary and M2 is secondary. Then next one, write the relationship between the number of turns in M1 and M2 coils if the transformer is to be used as a step down transformer and a step up transformer. What is a step down transformer? Voltage decreases. To get a step down transformer, M2 secondary one should be lower than primary one, right? This is step down. Step up means M2 secondary rounds larger than primary rounds. This is a step up. This is a step up. Write down an instance of using step down transformers in day-to-day life. So talking about step down transformers, you know in our grid, we have 230 voltage. We have 230 volt. We have 230 volt in our main grid in Sri Lanka. Okay. We have a 230 volt running in our main grid in Sri Lanka. But it goes down, it falls to Maybe you take your mobile phone charger, it states 5 volts. Sometimes your laptop adapter, 12 volts. Everything you use is 5 volt or 12 volts. Everything. So we should bring this 230 volts down to 5 volt, right? We should bring, when we take from our plug points, when we take current from our plug points, we get 230 volt. But you should get 5 volt. We need a step down transformer. That's why you have a small adapter. You don't connect your mobile phone using 2 wires directly to plug point, right? Just like you are connecting the iron. In the iron, you have the plug point, then directly the iron, right? That's all. You don't have an adapter in between, charging adapter or something like that in between. You don't have in your iron, right? You directly connect it to 230 because iron works with 230. But you don't connect your mobile phone like that, right? Directly to the plug point. You have a charging adapter. You have a charging adapter. You connect the adapter to the plug point, then you take a wire from the adapter. You connect the charging adapter to the plug point, then you take a wire from the adapter. In the adapter, you have a step down transformer. Okay? In the adapter, you have a step down transformer. Clear? Okay? Then where do we use step up transformers? In turbines, when in our power generating systems, before sending it to the grid, we step up them. Okay? I mean, take like power stations, diesel power stations, hydro power stations, there they produce a certain voltage. They convert this into a huge voltage before sending to the grid. So close to our power plants, we use step-up transformers. We produce a weak voltage, we need to produce a higher voltage from this. We use step-up transformers, and the voltage we produce at stations, power stations, we convert them to very high voltages at our power plants. Then we send them through the grid. Sometimes we convert it into 10,000 volts and send through the grid. Then you have some transformers there on the road, huge transformers. They step down them from 10,000 to 230. You can see in the road there are transformer box. Okay, okay, there are transformer boxes. Clear? They step down them from 10,000 to 230. Then you get 230 in your sockets. In your home, in your power sockets, you have 230. Then our mobile phone adapters convert them to 5 volts. Again step down. Again step down them to 5 volts. Clear? These are step up and step down transformer use cases. Okay? Clear? Okay. So I'll stop the session here for today. Then I'll inform in the group when I'm doing the electronics 1, 2. Okay? When I'm doing the electronics 1, 2, I'll let you know in the group. Okay? So immediately, okay, maybe in this week also I'll be doing some other sessions. In next week also we'll be doing some other sessions. Okay, sessions will keep happening. You can go through the tute provided by us to get more like understanding about physics and to do some questions. We'll provide the answer script for that tute too. Please join the group. Okay, and our number is not 70. Contact this number for anything. 1546825. Not 7015468825. So like I'm basically teaching A-level physics. So what I'm trying to do is you have a nice bunch of knowledge in A-level physics that could help you in O-level science syllabus. Okay, I mean the understanding is better when you have a thorough knowledge. Okay, so that is the target here. That is the target here. So just go through the tute, okay, but we are making sure that we are staying in the O-level scope, but we use the knowledge from A-levels too to make you understand things better, okay. That is the idea, to make sure that you understand things better. So make sure you are joining the groups, and more sessions will happen in the group. So whenever we put a message in the group, check that, and the recording will also be available in the group, okay. So yeah, thank you for joining, and the next session will be informed quickly today or tomorrow, okay. Thank you. And tomorrow you have the Sinhala medium session morning, same time. Thank you. Thank you for joining.
Thank you, Subhash.
Thank you, sir.
Thank you.
Thank you, sir.